Electric force, Coulomb's law. Remember earlier on where we had a plastic ruler and we rubbed it with some fur and it obtained a charge and then it attracted neutral bits of paper. Let's look at it more closely and see what happened. So we're going to start with two rods here. We have rod A, which is neutral, and you can see that it has an equal number of negatives and positives. That's how we show that it's neutral. And we have another rod over here, rod B. See how we have more negatives there? That's telling us that it's a negatively charged rod. And they're very far apart. The question is, what happens to the charges on rod A when we move it closer towards rod B? When rod A, this one over here, is brought closer to rod B, the electrons, or the negative charge carriers in rod A, will be repelled by all the negative charges over here. You can see we have a preponderance of negative charges there. So the negative charges in rod A will move to the left side, and so when the negative charges move to the left, you're left with a net positive charge on the right. And remember, it's the electrons that are moving here, certainly not the protons. So what we have now is a polarized rod. We still have a neutral rod here. Rod A still has an equal number of negative and positive charges, but the negative ones are to the left, positive are to the right. And again, we call that polarized. We now have the positive charges on the right of rod A closer to rod B than its negative charges. So it will feel a net attraction towards rod B. And it will move towards rod B when we let it go. We can just let it go here now without pushing it, and it will move on its own and be attracted to rod B. Newton's first law, which we first studied in dynamics, the law of inertia, states that objects at rest tend to stay at rest unless an external net force acts on the object. So this, of course, would be a special case of the overall law where objects in motion tend to stay in motion. In this case, we're just going to start with an object whose velocity is 0, so it's going to stay at rest. But what we see happening here is the free rod, that's the rod over here, which we called rod A, is moving. So there has to be a force present. We don't see it, but it's moving, therefore by the first law there's a force. We will call this the electrical force. And, as with all forces, it will be measured in newtons. In the late 18th century, several physicists, Joseph Priestley, over here, and John Robison, over here, reasoned and measured. Here, Robison, that's the important thing. Physics is all about measurement, and that was John Robison's contribution. And they found that the force between two objects followed the same principles as a gravitational force, and that the force between two charged objects depends on the inverse square of the distance between them. It's a 1 over r squared force, just like gravitation. In 1785, Charles Coulomb published a paper. It was based on detailed experiments. Again, fundamental part about physics. It's a measurement science. This definitively proved the 1 over r squared dependence, and also found that the force was proportional to the size of the charges. He used a torsion balance, which was based on the same principle as Henry Cavendish's experiment that measured the gravitational constant. Here's the equation, which is Coulomb's law. The electrical force is equal to K, which is a constant. It's Coulomb's constant, and it's 9 times 10 to the 9th Newton meter squared per Coulomb squared, times the absolute value of the net charge on one object, and Q2, the absolute value of the net charge on the other object. R12 will be the distance, notice it's not R12, it's R12, is the distance between objects 1 and 2 if they are point charges, or between the centers of the objects if they are spherical objects. Please note the striking mathematical similarity to Newton's law of universal gravitation. And again, we're just finding the magnitude here. The direction, we have another way of looking at that. We'll be using Coulomb's law to calculate the magnitude of the force between charged objects. And again, using Newton's third law this time, another Newton's law, but his third one, Each object exerts the same force on the other, except in opposite directions. So, Newton's third law applies to all forces, not just mechanical ones. Since electrical force, like all forces, is a vector, you need to specify the direction of the force magnitude determined by Coulomb's law. We'll do this by looking at the signs of both charges, remembering that like charges repel and opposite charges attract. Here's where it's different from gravity, right? Because the gravitational force is always an attractive force. The electric force can be either repulsion or attraction. Comparing the two forces. Both the electrical force and the gravitational force use a similar mathematical formula, and the magnitude of the force goes down as 1 over r squared. Electrical force can be attractive or repulsive. Like charges repel, opposite charges attract. The gravitational force is always attractive. And this is really cool over here. The electrical force is on the order of 10 to the 36 times stronger than the gravitational force.